All right, so let's try applying this. Let's start with some simple questions that you see on the screen here. First, the simplest question of all, which we should be able to answer easily. If I just take an object and I release it from a certain height, what will be its speed when it hits the ground? Now, of course, this is already, all of these actually are already questions that we know how to answer using kinematic equation-based methods, but now we want to learn how to answer these questions using energy-based methods. The reason being that energy-based methods can also often get you to the answer a lot quicker. Not always, of course, but often. These questions are simple enough that you can do them either way. So maybe I'll show you both ways. Anyways, okay, so first one. We have a ½ kilogram ball dropped from rest 2 meters above the floor. How fast will it be moving when it hits the floor? So step one, identify the system and the types of energy we're studying. The system is the ball, and the types of energy I'm going to need to keep track of here are kinetic energy and gravitational potential energy. Now we identify the initial and final states and sketch them. So the initial state, we're going to have, there's the ball, okay, there's the ground. It's released from rest. So it's at rest in this picture, and it's 2 meters above the ground. And the final state is going to be, it hasn't quite touched the ground yet, but it's about to hit the ground, traveling at an unknown final velocity. Let me call it V1, since this is part one of the problem. Okay, so there's my initial state, there's my final state. The next thing I need to do is write down the energy for the initial state and write down the energy for the final state. So for the initial state, we have kinetic energy equals 0 because it's at rest. What about the potential energy? Now, here's where that h equals 0 point comes in. Before I can write down the potential energy, I need to make a choice. I need to choose where am I going to call h equals 0 for this problem. In this case, it's probably pretty obvious where you're going to put it. Almost everyone would instantly think I'm going to put it at ground level. But you just need to realize that you put it there. I would mark it in your picture like that. There's h equals 0. Anything above that line is a positive h. Anything below that line is a negative h. So in this case, I can see that my ball starts out 2 meters above h equals 0. So I have h equals positive 2. Oops, change the width of my pen. Here we go. Okay, so h is positive 2 meters. So that gives me a final potential energy. I'm using the formula mgh. So that will be, my m is 0.5. My g, I'm not writing my units here, but this is all SI units. H is 2. And so this is, I can do that one in my head. That's going to be positive 9.8 joules. So the initial kinetic energy is, oh geez, I made a mistake here. Sorry about that. These are, of course, all initial. These are all initial values. Okay, so the initial kinetic energy is 0. The initial potential energy is 9.8. Now, final state. In the final state, I'm going to be calculating the kinetic energy using the formula 1/2 mv squared. Okay, m is 0.5 kilograms, and v is just v1. So I'll plug that variable in there. Then for the final potential energy, don't jump to any conclusions about what it is, but I can get it just by plugging in my value of h. Actually, let me do that step by step just to make sure that you see where I'm going with this. So I'm going to have the final height is 0. And again, why is the final height 0? Because I decided that ground level was h equals 0. The ball is now at ground level. So therefore, H equals 0. So that means that the final potential energy is going to be 0.5 times 9.8 times 0. So the final potential energy is 0. Okay. Now, all I have to do is set the total initial energy equal to the total final energy. So we'll have 0 plus 9.8 is the initial energy. And the final energy is 1/2 times 0.5 kilogram times V1 squared plus 0. So that means V1 is going to be 9.8 times 2 divided by 0.5 square rooted. And that gives me 6.26. Now remember, this method is actually only giving me the speed. So the speed is 6.26 meters per second. If you want this to be a velocity, you would have to know to put a minus sign in front of it, because you can see from the picture that it's traveling downward. So it has a negative y component. It has a speed of positive 6.26 meters per second and a velocity y component of negative 6.26 meters per second. Okay. Now, one thing I want to show you really quick here, just for the sake of comparison, is you also know that you could have solved this using the kinematic equations. You hopefully remember from earlier in the course how to do that. Let me go through that just to show you that it gives you the same answer. If you were to solve this as a kinematic equation problem, what you would do is you would list off your kinematic variables. So you would say initial velocity is 0. Final velocity is my unknown that I'm solving for. You would have acceleration is gravitational acceleration minus 9.8 meters per square second. You would have delta y is negative 2 meters because it goes down by 2 meters. That's enough information to pick a kinematic equation. The right one to choose would be VF square equals VO square plus 2a delta y in this case. So then I'd have VF squared equals 0 plus 2 times 9.8 times 2. The negative signs cancel out. So I do 9.8 times 2 times 2 square root. And lo and behold, I get exactly the same answer. So again, this energy content is actually not giving you different results. It's not like it's something new which is replacing Newtonian physics. It's just supplementing Newtonian physics for cases where this method maybe is easier to use than the Newtonian method, which is often the case. Okay. Anyways, so let's do the other parts of the problem. Do a little bit of erasing. The next part of the question is, instead of dropping the ball starting from rest, you throw the ball upwards, and you want to know how high does it go. Another question which is answerable with kinematic equations or with this energy-based method. Okay, so first we want to draw the initial and final state. So it's thrown upward from ground level. So that means now the ball is at ground level, thrown upwards at a speed of 10 meters per second. And the final state is going to be that it reaches maximum height somewhere up here, a height, let's call it h above the ground. And when the ball reaches maximum height, if it was thrown straight upward, it's momentarily at rest. That's the same statement we used to make in kinematic equation problems all the time, that when the ball's at the peak of its trajectory, the y component of velocity goes to 0. So there's my initial and final state. In my initial state, I'm going to have kinetic energy equals 1/2. I'm going to go a little bit faster this time. mv squared would be like this, and that's going to be 1/2 times 1/2 times 10 squared would be 25, I believe. And initial potential energy, again, before I can say my initial potential energy, I have to make sure I know what I'm calling h equals 0. You know what, just for illustration purposes, let me not set h equals 0 equal to ground level this time. Let me be a weirdo and choose h equals 0 to be up here. Why not? Okay, so h equals 0 is actually up at the peak of the trajectory. So I don't even actually know where I'm setting h equals 0 to be, because it's at wherever it ends up at the end of the problem. All right, I just want to show you that this will work. So because that's where I set h equals 0 to be located, what is my initial value of h? Let me actually start there before I write down u. What is my h0? Okay, so first of all, you'll notice that my initial object there, it's below h equals 0. Everything that's below h equals 0 down here has a negative value of h, and anything that's above h equals 0 has a positive value of h. So my h value is actually negative, which might sound weird, but it shouldn't sound weird. This is really the same thing as saying, like, when you use coordinate axes, like anything that's below your origin has a negative y value, anything that's above your origin has a positive y value. It's the same statement. Anything that's above what you're calling h equals 0 is positive. Anything that's below what you're calling h equals 0 is negative. So it's actually negative h, because it's h below my reference point. I want the variable capital H to be a positive number. And then I calculate my initial potential energy here using the formula. So it's M is 0.5, G is 9.8, and then I have negative H plugging in here. So you notice my initial potential energy is negative, which seems weird, but it's fine. Potential energy can be negative. It's no big deal. Just live with it. So that means my initial energy is actually 25 minus 4.9h. It's a somewhat complicated expression. Okay, what about my final energy? Final kinetic energy is 0 because the object is at rest. Final potential energy is 0 because my final h value is actually 0 with the choice I made. Because no, h equals 0 is at the peak of the trajectory. That's how I defined it. So therefore, it's at h equals 0. So actually, weirdly, in this setup, the energy, the total energy of the system is actually 0. That doesn't mean anything. It just is what it is. So when I set my initial energy equal to final energy, my initial energy is 25 minus 4.9h. And my final energy is 0. And you'll notice the total energy in the system is 0, but it's okay because in the initial state, the kinetic energy is positive, the potential energy is negative, so they cancel each other out and give you 0. So then I end up getting h equals 25 over 4.9, which is 5.1. meters. Okay. And just to prove to you that this works, let me once again just also do it with kinematic equations really quickly, just to show you that it gives the same answer. And also just to show you that putting your reference point in a weird location like that also gives you the right answer. So if I were to solve this with kinematic equation based method, what I would do is list off my kinematic variables. Initial velocity is positive 10. Final velocity is 0. Delta H I mean, delta y is h. That's my unknown. I have gravitational acceleration. So acceleration is minus 9.8. With those four variables, my equation is once again going to be this guy, delta y. So I'm going to have 0 equals 10 squared plus 2 times negative 9.8 times h. So I'm going to get 100 divided by 2 divided by 9.8. And miraculously, it does, in fact, give you exactly the same answer. Okay. Now, I think I'm going to forego doing the third question there because this video is getting pretty long. You can try that one on your own or follow along in the lecture note packet. But hopefully you get the idea of how to solve these problems. Just systematically go through and solve them all using the procedure. The only thing you have to keep in mind is that be careful about setting your h equals 0 reference point, and you'll be fine.